From the Library of Congress in Washington, D.C.
This is actually a real treat for me to be able to introduce Janna Levin, who's written just a beautiful book, fascinating book called Black Hole Blues and Other Songs from Outer Space. Janna Levin is a professor of physics and astronomy at Barnard College of Columbia University. She has her PhD in physics from MIT. She's written a couple other books, How the Universe Got Its Spots, and she wrote a book called A Madman Dreams of Turing Machines. This book, I know probably many of you in this room heard about the whole LIGO experiment earlier this year, the gravitational waves. Who here knows about that? Good, okay, so we got some nerds here, some geeks. 100 years ago, Einstein predicted that the universe would resonate with these gravitational waves as space itself kind of rippled from the collision of super dense objects. And for 100 years, people try to figure out, how do we detect this? It's an amazing story. Now, if Einstein were here today, he probably would say, you know, I was right. You know, you didn't need to check it. I mean, I got this. You know, I mean, I'm sure, right? But experimentalists wanted to check it out. And so back in earlier this year, there was this big announcement down at the National Press Club where they had detected these gravitational waves with this experiment called LIGO, which is actually two enormous experimental detectors, one in Louisiana, one in Washington State, that were set up with incredible precision to measure the very tiniest change in space itself as a gravitational wave passed through the Earth. And they've been working on this for 40 years. And I'm a reporter for the Post, I'm a science reporter, so I went there, we wrote about it, it was a big deal. And there were some legendary physicists there. Ray Weiss was there, Kip Thorne was there, and we threw together our stories. Well, now Janna Levin comes along and gives us the real story, the backstory, and it's beautifully written. It's told me all kinds of stuff I wish I had known earlier this year when I covered it for the newspaper. I told Janna I'm very resentful when a scientist writes so well. I mean, why do I exist if, you know, I mean, we count, if you're a journalist writing about science, you count on scientists being utterly incomprehensible, right? You count, you know, and then you translate it, you know, it's like, what she means to say is, you know, but this book is so well written, and so please give a warm welcome to Dr. Janna Levin.
Well, I wasn't going to stand behind the podium because I'm so little. Hold on, I'm going to try to do this with the mic. Well, that was basically my entire talk. So what do you guys want to talk about now? Thank you so much for coming out. I'm really honored everyone came out. I'm here at book festivals as a fan as much as an author, so it's just an absolute bonus to see everyone out here for this talk. I know some of you raised your hands when asked if you had heard of the LIGO experiment. So on February 11th of this year, an obscure experiment that almost nobody had ever heard of announced what has been touted as the scientific discovery of the century. It was an early morning press conference, and people were listening all over the world, and as soon as the press conference started, the New York Times, I was sitting next to Dennis Overby from the New York Times, pressed, you know, submit on his article. And all of these articles went straight to the front page of all the papers. It was for 24 hours. It was like the whole world stood together and stopped and listened. I was on Al Jazeera TV that night, and I'm looking down the barrel of this sort of, I'm in a tiny box talking to somebody in Qatar, I don't know where, and you know, and there's this moment where they're looking at me and I'm looking at them, and they're saying, they're about to ask me what does this mean for humanity? And then they're like, I'm sorry to interrupt you, but we have to turn to the war in Syria. So there was like a second where everyone paused for something other than our kind of earthly concerns. And yet after about 10 minutes, I felt like people weren't sure what exactly it was all about, right? How many people, after they heard the announcement, felt an hour later that they didn't really understand what the hell it was all about? Oh, come on, there's more of you than that. I don't believe that for a second. It's a very difficult result. It's something we've never done before in the history of humanity. When LIGO, this experiment, which again, no one had ever heard of, came online and made the discovery, what you don't know, or maybe some of you know, but I'm assuming many don't, is that it was a 50-year arduous climbing of a kind of scientific Mount Everest, that people gave their careers over to this campaign. It cost nearly $1 billion. It consisted of two absolutely colossal machines, one in Louisiana, one in Washington State, each one spanning 4 kilometers. And they had failed in their initial generation. I mean, failed is maybe too strong. The initial generation of machines was built in 2000 and heard nothing. What LIGO did was not take a picture of the sky. These are not telescopes. These are recording devices. It recorded literally the shape of space-time ringing from 2 black holes 1.3 billion years ago colliding. And what I'd like to do, more or less for the rest of my half hour or so, is pick apart what that discovery meant and what happened and why it's so significant. So let's see if our technology is working. I'm going to play for you the recording. And this is, we're just going to listen to it for a second, and then we're going to spend the rest of the time trying to understand how this is possible. So LIGO Hanford, the instrument, ooh, that's loud. And that's LIGO Livingston in Louisiana. And so what the hell is that about? I mean, what does that even mean? What does that even mean? How many of you are like sci-fi fans who know that there's no such thing as sound in empty space? If you watch a sci-fi movie and you see somebody screaming in the vacuum, you're going to be totally annoyed, right? There's no sound in empty space. How can this possibly be sound? And I'm going to argue to you that this is literally something we could hear, but it's incredibly quiet by the time it gets to the Earth. So let's do a little picking apart of what this discovery was actually about. This is a view of our Milky Way galaxy taken from the European Southern Observatory in Chile. It's this dry, barren bit of brittle Earth, and that's perfect for astronomical viewing. The skies are dry. It means there's not a lot of interference. You can just look out. This is taken just with a digital camera. If you can imagine holding your eyes open long enough, you could see this. The Milky Way is this spectacular riff on the sky. And if you think about where we really are in the galaxy, we live in the galactic suburbs. New Yorkers are always terribly offended by that fact. They really resent that, but we do. We live safely outside the center of the galaxy in the galactic suburbs, and this is the view from our sky, the Milky Way. The reason it looks like it does is because we live inside it. Okay, we can't look at it from the outside. There's our star. It's a pretty average star. It's a yellow star, and as we all know, we're the third rock from the sun. There's 100 billion stars in the Milky Way galaxy, and there's probably tens, at least, billions of planets like ours. But we've never gone anywhere, and we've been to the moon. So this thing about putting a flag on the moon, that's real. That's not a conspiracy theory. We have been to the moon. But our biggest aspiration right now is just to go to Mars. It's our galactic, it's our solar neighborhood. We've barely gone anywhere. And so if you think of being so confined to this tiny region outside our rocky planet, the galaxy itself, the center of the galaxy is 26,000 light years away. The whole galaxy is 100,000 or so light years across. And we've only gone to the moon, which is seconds away in terms of light speed. And so here we are confined to this little solar neighborhood, and almost everything we know about the universe is brought to us by light. We wait patiently, we build telescopes, and we take pictures of the sky. This is not a cartoon. This is an actual map of all the galaxies we've ever discovered in the universe, the observable universe. There are as many galaxies in the sky as there are stars in our own Milky Way. So there are hundreds of billions of galaxies. Everything you see in this map is an entire galaxy. And we collect this sort of map of the universe by taking pictures. You know, ever since Galileo pointed a telescope at the sky, we've made this kind of silent movie, right, of these collected snapshots that date back 14 billion years and stretch over 90 billion light years across. It's really an incredibly extraordinary image. Yet, all of that stuff, all of it, in the entire observable universe, everything we have ever seen, including everything we see on this Earth, everything in this room, everything out in the farthest reaches of space, make up less than 5% of what exists in the universe. More than 95% of the universe is in dark stuff, stuff that can't be seen, dark matter or dark energy. And it will never come to us through light. And that's really quite a stunning realization, to understand that as vast and spectacular as the universe looks to us in pictures, it's a very modest fraction of what's out there. My favorite terrain of the entire cosmos is the darkness, you know, the vast emptiness of space-time, the darkest parts of the universe. This is a portrait of a black hole. I'm proud to say I did that myself. A black hole, you know, black holes are out there. We see them indirectly because they destroy their neighboring environments. But there's many, many black holes that we don't see. There's probably 1 billion black holes in our own galaxy, and we only see a handful. The center of our galaxy has a black hole 4 million times the mass of the sun, and we only know it's there because of the orbits of the stars in the inner system. It's completely dark. This is what a black hole would look like if we could see it up close. If some evil civilization figured out how to collapse the sun to a black hole, it would collapse down to 6 kilometers across. Isn't that spectacular? The entire mass of the sun in 6 kilometers. I know all my references are New York-based, but you're going to have to forgive me. That would fit in Manhattan. You could fit that black hole in Manhattan, but then it would destroy the Earth. So that wouldn't be a good idea. But this is also an illustration that black holes have this kind of horrible reputation as engines of terrible destruction, but actually you'd be perfectly safe in orbit around a black hole sun. Isn't that like a song? Is that Soundgarden? You'd be perfectly safe in your orbit around a black hole sun. There's nothing wrong with your orbit. It's exactly the same, in fact, as the sun's pull on a gravitational pull. The only problem is it would be apocalyptically cold and dark, and that would be really unfortunate. But in this computer model, which was made by Andrew Hamilton from Colorado, the little Earth model is kind of self-illuminated. But that black hole is only 6 kilometers across, so that's a tiny little pseudo-Earth satellite. Oh, sorry. Did I do something bad? I did something bad. I'm back. Thanks. But the important thing to notice about this is that what the black hole really does, even though it's dark and we can't see it, is it creates curvatures in space-time itself. And that means that even light bends when it travels around a black hole. So notice that while this Earth passes behind this black hole sun, you can still see it. You can still see it because the light gets lensed back at you. We've never seen anything like this in reality. We can't see black holes like this. There is an experiment to try to measure the dark shadow of a black hole in the center of our galaxy. It's 4 million times the mass of the sun, but it fits in a handful of sun widths, which is crazy density of mass, but it's 26,000 light years away. And there's an experiment that uses essentially all of the telescopes on the Earth to try to resolve the shadow. It's equivalent to trying to resolve a quarter on the moon. And I really believe this will be successful in the next year or so. I think you're going to be seeing the first actual pictures of a black hole that we've ever seen in the history of humanity in the next year or so. If there was a black hole between us and the Milky Way, what we just saw, this great rift of the Milky Way, and we were to try to fall into it, you were an astronaut orbiting around it, this is what you might see. The spectacular thing about black holes is that there's nothing there. I mean, people think black holes are these dense crushes of matter, but there's actually nothing there at all. If you fall across the shadow of a black hole, it's empty. It's empty space-time. Maybe you guys can ask me questions about that later if you want. But also, the other myth about the black hole is that they're completely dark. Black holes are dark from the outside, but not on the inside. If you were to fall into a black hole, you'd have a full, I don't know, microsecond of bright light falling in behind you from the entire galaxy. It would be like you saw the evolution and the history of the entire galaxy falling in behind you, and you could get this bright flash of light. These are, again, computer models and not cartoons. So as you fall towards the center of the black hole, all that light from the galaxy that falls behind you becomes concentrated into this bright flash of light. I used to jokingly call it a near-death experience. You know, when you see the light at the end of the tunnel, only it's like a total death experience because you get crushed to death in the center of the black hole. We don't really know what happens in the center. That's still a mystery. Does all the material that fall into a black hole get blown out into another universe? Is there another Big Bang inside the black hole? Is the black hole much bigger on the inside than it is on the outside? Is it as big as a universe on the inside? These are things we don't actually know the answer to, but are all conceivable possibilities. You know, Doctor Who's TARDIS, you walk inside and it's huge on the inside. That's like the black hole. It's 6 kilometers across on the outside, but it's an entire universe on the inside. It's not an experiment I recommend anyone tries. Okay, so here we are coming up to this great event that happened. When Einstein theorized about all of these things, the curvature of space-time and his most famous accomplishment, the general theory of relativity, it's like 1915, he finally writes down the correct mathematical expression for his theory of general relativity. And the first thing he turns to is the question of what he calls gravitational waves. He says, if an object can curve space and time around it, then when the object moves, surely those curves have to move with it. And he imagined they would create waves literally in the shape of space. If you were floating nearby a black hole and it moved, you would have to sort of bob on the wave, communicating to you, just like fish swirling in a pond, that this object had moved. And he labored over this for years. This was 1915, 1916. In 1930s, when he was asked, are these gravitational waves real? Einstein said, I don't know. You know, I really don't know. He would write a paper saying they do not exist. It would be accepted for publication. Between acceptance and publication, he would sneak in a completely different paper that said that they do exist, you know. And then people would say, Einstein, you've got to be very careful. Your famous name is going to be on these papers. And he would say, my name is on a lot of wrong papers. Just don't worry about it. It's not his concern. But this debate went on into the 70s. But I'm going to show you a very sophisticated current model of what happens as two black holes collide. This is, again, a computer model. And what it's really showing you is those natural curves in space-time around the objects. And as they orbit, it makes a wave, and then they collide and form a new black hole. That's the current thinking. And that flattens out space-time, and eventually that black hole goes quiet. Now, what does this have to do with sound? Oops, sorry. That was abrupt. What does this have to do with sound? The argument is, if you were floating nearby those black holes, you would literally hear them, even in the absence of air, even in vacuum, because the space-time changing would squeeze and stretch you as it passed. And because your eardrum is built to resonate in response to being squeezed and stretched, you would literally technically hear the waves, even in the absence of air. It happens that the two black holes that collided, that were detected in September, ring in the human auditory range. It's just a ridiculous coincidence that it's literally in the human auditory range. This is a model from my group where we show in yellow the orbit of one black hole, in red the orbit of another. This is just a theoretical prediction, and simultaneously play for you what you would hear if you were floating dangerously close to those. Might be a little loud because it's going to get louder. Notice you can hear details of the orbits. It's like mallets on a drum, banging a drum. You can reconstruct the size and the motion of the mallets by listening to the sound. Black hole orbits can be very complicated. Notice how it gets quiet and loud. It's gonna get quiet again. These are things that allow us to reconstruct the size and motion of the mallets by listening. That little chirp at the end is really goofy. Everyone laughs at that because everyone thinks black holes are going to sound way more butch than they actually do. They just sort of have this like sort of little effeminate chirp at the end there. But that chirp is extremely characteristic of black hole collisions. Extremely characteristic. What's happening is the black holes begin to orbit so quickly in the final fraction of a second. They're orbiting near the speed of light that the frequency at which they're banging space and time, the drum, goes up. And it creates this sort of scooping up chirp right before it goes quiet. And it goes quiet because they create a new black hole and go silent. So in walks Ray Weiss, who was mentioned in the introduction. So let's take us to the 1970s. It's the 1970s. People are still arguing about whether or not black holes are real. They're still arguing about whether or not gravitational waves exist at all. Ray Weiss is a young professor at MIT, and he's asked to teach a class on gravitational waves. I'm sorry, on Einstein's theory of general relativity. And he's just started a new gravity program. He's this young professor. He's really, wants to make a good impression, and he knows nothing about general relativity. So he says yes. So he teaches his class on general relativity, and he says he was bumbling. He was completely bumbling. He couldn't follow the mathematics. He didn't understand the theory. It was incredibly difficult. And all he could make sense of was this thing about the gravitational waves, that he could just imagine, how could I make that seem real? If a gravitational wave, like a wave in the ocean, passed, and something bobbed on the wave, you could measure it. And he's an experimentalist, and so he's dreaming of ways to measure this, the gravitational wave, and that's the thing that keeps the students in the class. He says they're not walking out. They're not walking out because he's thinking about real ways to understand it. And he comes up with this idea. He calls it a haiku. It's for this little instrument. Here's the idea of the instrument. You shine a laser, which was new at the time, down this L-shaped instrument. It gets split at that beam splitter there and shines to the two mirrors. Let's watch it again. Those little black circles at the end are two mirrors that are hung so delicately that if a gravitational wave passes, they'll sort of bob on the wave. And if they move because of the gravitational wave, the laser will keep track of their movement, and it will record the passing gravitational wave. Now, you don't have to worry about the details of the experiment. You can think of this as like the body of an electric guitar. If you pluck an electric guitar string, technically it doesn't really make a sound. You need the body of the electric guitar to record the shape of the string. You plug that into an amplifier and you play it back as sound. In many ways, LIGO is like a musical instrument. It plays the wave back as sound. So Ray starts to build this in what's known as the Plywood Palace at MIT's campus in the 70s. It's a ramshackle structure that was thrown up on the periphery of the campus during the war effort, the World War II effort, in an attempt to get scientists invested in technology important for the war. It was supposed to be torn down within 5 years. It existed for 50 years. And it was as though the sheer crappiness of the structure encouraged creativity. 9 Nobel Prizes came out of the Plywood Palace, and this may be the 10th. Ray builds this tiny little prototype. It's 1.5 meters long, tiny little prototype. His colleagues are telling him, nobody cares about what you're doing. It's not important. This will never succeed. Black holes aren't real. Gravitational waves don't exist. And they said, even if they did, if the sun blew up and created a wave in space-time, you could not hear it with your machine. We'd do better looking out the window. And it was true. You'd do better looking out the window. And Ray realized that he had to build the real instrument. It was 3,000 times bigger than what he was doing in the Plywood Palace, with no financial support, no community support, and he thought he was doomed. He told me once, I started life with one ambition. I wanted to make music easier to hear. He was an immigrant from Germany in the 1947. He was a kid building hi-fis, and he would lug speakers that he found in an old Paramount movie theater that had been burnt out. He would lug them home to Manhattan, and he would build these little circuits, and he would have all the immigrants in the neighborhood come over and listen to the Philharmonic, and this was his life's ambition. And in some bizarre twist, he has this ambition as an adult to become the one who records, the symphony of the skies in some sense, right? And he sees this dream of his passing because he doesn't have funding and he doesn't have support. And other people start to hear about his idea. In Germany, in Japan, in Scotland, they start to build these machines better than his, bigger than his, more likely to succeed. And Ray says to me, I thought that was it. And then the next big event is I met Kip. And Kip Thorne is a famous and iconic astrophysicist. And they teamed together. I'm going to fast forward in the interests of not keeping you here all night. But fast forward to the year 2000, they've accumulated a team of almost 1,000 people. And they've secured hundreds of millions of dollars from the National Science Foundation. They've fought bitter, grievous battles. People have literally, like climbing Mount Everest, there are like bodies along the way. It's gruesome. But they get there. In the year 2000, they build these instruments. This is the real LIGO machine, the one that's 3,000 times bigger than Ray's. They're these L-shaped machines. Along those tubes is a vacuum. They're the two largest holes in the Earth's atmosphere, if you add up the LIGO machines. There's less stuff in those tubes than there are in regions of interstellar space. This is a little cartoon. We're going inside the tube, and the laser shines down the tube and hits a mirror 4 kilometers away, and bounces off the mirror, keeps track of its location. So if the mirror is bobbing on the wave, it will know that it has bobbed on the wave. In these, what we call beer chambers, are these elaborate components. Now, in the year 2000, all the science runs, they heard nothing. The first generation of machines were completely quiet. And you can imagine the community response to this initial generation. But they weren't that surprised on the LIGO team. They always argued it would probably be a second generation of machines. The idea is that each machine has to make a recording or you would never believe it. And how it works, something happens, some cataclysmic event far away, and it washes over the Earth and rings the two machines. This is what the machine sounds like. It sounds like noise. They literally listen to the instrument in the control room through like conventional speakers. This is, a process every day. My friend Rana Adhikari, who's one of the important experimentalists on the team, says he gets really pissed off if the speakers aren't on when he goes into the control room. Then in August, this happened. Forgot this. The Washington machine is on the same site as the plutonium separation facilities that were used in World War II for the first bombs, the ones that were actually used in Japan. And that's because they have to be on a remote site. It's a government facility. There's no association with the plutonium separation facilities, but it is kind of ominous. You can see them in the plumes on the horizon. And because they are nuclear sites, they have a lot of security, and I guess one of the security guards is driving around in the middle of the night in this desert with a very, not completely thoroughly flushed out knowledge of the local geography, and he drives into one of the arms. And I know this is not a nice thing to say, but luckily he broke his own arm and not the LIGO arm. Had he broken the LIGO arm, not only would the experiment have been over, people told me, that's it, we would have gone home. Drawing the vacuum is so hard. That vacuum was drawn in 1998 and has not been brought up to atmosphere since. If that vacuum had been blown, as one of my friends on the team says, Mike Landry, he says, we all would have gone home. That's it. It's over. But not only that, he would have suffered much more damage, presumably, than just breaking his arm. It's like opening a door in the space station, right? Only the vacuum's on the inside, not the outside. But it would have been very, very dangerous for him to blow a big hole in that vacuum very suddenly. At one point, they discussed not even building that cement encasement. Luckily, they did. So at the other site in Louisiana, they were shot up by some hunters who people think that was not an accident, that they were unhappy about this scientific experiment on their hunting grounds. So one of the head of the Louisiana site says, we're so American to the Europeans. You know, we've had a car incident. We've been shot at by guns. All we need is a hamburger incident, you know? So in August 2015, this is 15 years after the initial machine was built. This is 50 years after Ray started this experiment. Ray works on that experiment all the time. I cannot tell you how many times somebody said to me, we better ask Ray. Ray walks those tunnels. He finds wasp and vermin, and the chlorine from the urine is rotting the tubes, and he's the one who discovers all this stuff. I mean, he's really in the experiment all the time in his 80s. Ray says to me in August of 2015, if we don't discover black holes, this thing is a failure. It's $1 billion into it, and really most of his life. And the reason he said that is that all the old-timers, they're after pure space-time coalescence. That's what they want to discover. Nothing else will compare. Meanwhile, all of the other experimentalists, including a lot of the young people, are telling me nothing until 2018. Don't expect anything until 2018. Meanwhile, the funding, they're right on the edge of the funding being not retracted, but it becoming a more difficult argument to make that this experiment should continue to get funded at this level. A lot of the astronomy community is unhappy and against it, doesn't think they'll ever succeed. So 3 weeks later, after this conversation, it's September 13th, the weekend, and Ray's working on the site, and he's looking for radio interference, and they decide that they're not ready to start the science runs yet, and they're going to keep testing the machine. But he says, luckily, my wife said, it's time for you to come home. So he gets on a plane and he goes to Maine. It's late Sunday night, early Monday morning, and a lot of the team at Louisiana and in Washington are still doing these tests. They're banging on the machine. They're driving trucks up and down the access roads, braking really hard to try to knock the machine, what they call out of lock, which means that it's in observing mode. And eventually, 4 in the morning, Louisiana, 2 in the morning, Washington, they decide, this is ridiculous, we're tired, we're going home. They put down their tools, they go home. Within an hour, they leave the machine in observing mode. Within an hour, on Monday, September 14th, after a 1.3 billion year journey, a gravitational wave comes from the southern sky. It rings the machine in Louisiana, is captured beautifully. 7 milliseconds later, skimming across the continent, it rings the machine in Washington State, is captured beautifully. By the time Ray wakes up at 8:30 Monday morning, looks at the log and says, what the hell is going on? It's already billions of kilometers away. And this is what they detected. This is a computer simulation. No telescope could record this. They detected the collision of 2 black holes. One was 36 times the mass of the sun. One was 29 times the mass of the sun. They heard the final few orbits, 1/5 of a second. This is drastically slowed down so that human beings can perceive it. Each black hole is a couple of 100 kilometers across. They were traveling near the speed of light in their final orbits. They caught that, let's see it again because it's so beautiful. They caught the last 200 milliseconds, 1/5 of a second, before those 2 black holes collided and merged to make one black hole about 60 times the mass of the sun. That one black hole rang off all the imperfections and went quiet. And you can actually hear this in the recording. You can hear the black hole kind of shedding away the imperfections and going quiet. It was not only the first bare detection of black holes. You could never see this in light. It was the loudest single event we've ever detected since the Big Bang. More power came out of that collision than all the stars shining in the observable universe combined. And yet none of it came out as light. All of it went into the ringing of space-time, ringing the drum. And by the time it got to the Earth, it was so quiet that it moved the mirrors by less than 1/10,000th the width of a proton over 4 kilometers. It was just an absolutely minuscule, faintest, thinnest wisp of a sound that was finally recorded. So why don't we hear it again? And what you're going to hear is actually that final chirp that we've already predicted in our simulations. What's so stunning is that the simulations that people have been doing across the world internationally are so close to exactly what you hear. So there. So that is actually what they recorded. And by reconstructing from the sound, they deduced the size and motion of the actual mallets. And then just to close, since this is a book festival, I was gonna actually just read 2 very short paragraphs from the end of the book, if you don't mind, and then I'd be happy to take questions. I think I can do this with the podium. Hold on. I don't think it's a spoiler for me to read from the end of the book. You know what happens. They discovered gravitational waves. There will be press releases, scientific papers will be published, news articles will abound, there will be documents, reports, and careful records kept. We'll continue to send a portrait of our best selves into space, a declaration that we were here, that we strove for understanding, that we often failed and occasionally succeeded. We heard black holes collide. We'll point to where the sound might have come from to the best of our abilities, a swatch of space from an earlier epoch. Somewhere in the southern sky, pulling away from us with the expansion of the universe, the big black hole will roll along its own galaxy, dark and quiet, until something wanders past, an interstellar dust cloud or an errant star. After a few billion years, the host galaxy might collide with a neighbor, tossing the black hole around, maybe toward a supermassive black hole in a growing galactic center. Our star will die. The Milky Way will blend with Andromeda. The record of this discovery, along with the wreckage of our solar system, will fall into black holes, as will everything else in the cosmos, the expanding space eventually silent, and all the black holes will evaporate into oblivion near the end of time. Thank you. And I think I'm taking questions, but I don't know what the clock says. Oh, that's it? 5 minutes, sorry. Please.
Do we know the speed of...
Time's relative, by the way. Yeah.
Do we know the speed of gravitational waves?
It's a really important question. In Einstein's original theory, the speed is the same as the speed of light. We can tell that it took about the speed of light to get from the Louisiana machine to the Washington machine, but we can't measure it that accurately that we can say for sure that it is indeed traveling at the speed of light, but the evidence suggests that that's what's happening. Yes, I think we're going to trade back and forth.
You said that there was, like, absolutely nothing inside of the black hole. Does that mean the absolute devoid of atoms and everything in space?
Yeah, so technically the only way that we know how to form a black hole at the moment is through the death state of a star. So a very heavy star, much bigger than our sun, at the end of its life, when it runs out of fuel in its interior, it collapses under its own weight. It no longer has the sort of brightness and the pressure to stay aloft, and it collapses under its own weight. And remarkably, Einstein did not think that this would happen, but after studying nuclear physics involved in the bomb projects, they realized that there was no forces that could resist collapse. And the star will collapse under its own weight. Eventually, let's say it's 10 times the mass of the sun, that object, as it collapses, becomes like 60 kilometers across. At that moment, it creates the shadow, the region where the curvature of space-time is so strong, that not even light can escape. But it doesn't stop falling. The stuff keeps falling, and it falls all the way to the center. So the stuff is not there at that shadow. What we call the event horizon of the black hole is empty by the time it's formed. Where that material of the star goes once it crushes to the center, we don't know. Again, it might blow out into a new Big Bang inside the black hole, a whole universe inside there, or it might get stored in some kind of thing we don't understand, some kind of remnant. We don't really know what happens. But it's not there at the event horizon anymore. That's for sure. That we understand. Yes?
Kind of a science fiction question, like, because I was always fascinated, like there is this theory that like our conventional engines, they would never take us anywhere. It will take like hundreds of years to go to the nearest star. And there's this lovely theory that like with the black holes, we can actually maybe find some shortcuts. But like, would anybody actually survive going into like, because I remember reading those like endless fall, like people get stretched into, like.
Yeah, it's not a good story.
No.
Not a good story
So
on the
is
interior of a
there
black hole.
any-
It doesn't end well for anybody on the
So-
inside
so
there.
there's no really potential?
Well, here's what we know. We know that our current spacecraft, current technology has just broken out of the sun's influence. Voyager, which was launched in the 70s, has just barely escaped the influence of the sun, and that was from the 70s. It will be tens of thousands of years before it makes it to another star system. Our nearest star at our current rate of technology would take 35,000 years to send a spacecraft there. There are these things called nanocrafts, which are literally the size of like a postage stamp, and if we can accelerate those then they might get there in decades. But traveling at the speed of light, those star systems are only 4 years away, okay? But we don't know how to get anything near the speed of light. So the question is, could we use something like black holes as a, that's not terribly likely, but it doesn't mean, warp drive is something we can kind of try to make, like there are mathematical models of a better thing to do would be to warp space-time so that you pull the star closer, you walk across, and then you push it out again. That would actually work the best. Literally, you could get there in a fraction of a second, but we just don't know how to harness energy sufficiently. If we did, we wouldn't be arguing about oil and coal anymore, and fracking, if we knew how to harness energy like that. Do I have time for one more question? One more. Sorry for people in the line, but I can stay after.
Sure. I was just curious, in your mind, what do you think the coolest thing about this discovery is? Like, is it the fact that Einstein's theory of general relativity has been further validated, or that this is evidence of black holes, or even that this may be a precursor to even additional discoveries? I
think it's not that we've proven Einstein right again. I don't think anyone's surprised that gravitational waves are real, or that they exist. I think what's been much more exciting is that it's the first time we've ever detected black holes truly, in a sense, without looking just at stuff around them. Usually we look at what they're doing to stuff around them, and we say, oh, there must be a black hole at the center there creating all this havoc. This is entirely different. We are directly hearing the collision of these black holes. We've never seen two black holes together because you can't see them. And I think it points to the possibility that this is a completely new dimension in terms of understanding the universe, that this silent movie that we've compiled is now going to be accompanied by this soundtrack, and this soundtrack can get ever more complex and rich as we get more sophisticated at listening. And that's just, it's like pointing the telescope at the sky for the first time. That's what we hope, right? We hope that we're going to discover things we haven't even thought of before, because 95% of the universe is dark. And the only way we're going to detect it is by listening. So thank you very much. I'd be happy to sign books or stay after.
This has been a presentation of the Library of Congress. Visit us at loc.gov.